Thank you for the introduction. Today I'm going to talk about the tip-tap battery-free discrete 2D fingertip input. This is a collaboration work with Wang, Shan, Ningshan, Ouyang, Omid, Abari, and Daniel Vogel. So our motivation is to create a wearable input device that requires minimum movement for user comfort and social acceptance. However, most of the existing wearable input device requires battery or power cable to be attached. For the user comfort and convenience, battery-free is another key factor of a wearable input device. As a wearable input device for subtle hand and finger movement, many techniques have been proposed. Digit Space is a thumb-to-finger interface designed based on the hand anatomy and touch precision. However, their studies only evaluated predetermined position on the inside of the finger, and the side and back side of the finger usage was not explored. Fingerpad is a thumb-to-finger interface using a magnetic field sensor. It can capture very precise finger movement, however, the sensor requires external power source. RFID is battery-free identification mechanism used for various HCI researches. Rethinking RFID proposed various sensors using RFID. However, the size of the tag is the challenge when we want to adapt their techniques for small wearable devices. So these are not only related work, but represent three approaches related to our project. So our research question here is, can we create a wearable and reasonably expressive input technique that works without battery? We created tip-tap, which is a RFID-based wearable input device that can recognize 9 discrete positions on fingertip. It is a very simple structure, and it can be implemented into a temporary tattoo form factor. This on-skin version is low on the recognition range, but we also prototype on-glove version to extend its recognition range. I'm going to take you through the process that got us to this result. To design our tip-tap, we conducted 2 experiments. The first study is Readability Study, which identifies the reachable area of thumb to index finger taps. We recruited 8 participants and measured the height and width of the thumb pad. Then a participant tapped the index finger with the thumb pad with the ink pad. Then we traced the bound of the inked area and marked the finger joint and the side and the center of the finger. Then we repeated this for 7 thumb positions. After the trial, we cut out the index finger part of the glove and opened it from the middle finger side. Then took the photo image of the glove and scanned it. When we scan the image, we adjust the size of the image using the side and joint line of the glove. The red line represents the side line of the index finger, and the black line represents the front and back side of the finger. From this scanned data from all of the participants, we created heat maps for each thumb point. For example, from this heat map, we can say, with the center middle point of the thumb, all of the participants could reach the side of the index finger from top to down. We did this for all 7 thumb positions. From these 7 heat maps, we extracted thumb index interactions that is comfortable for all of the participants. For example, if we look at these 3 heat maps, we understand that with all 3 positioned at the center of the thumb, everyone could reach any part of the side of the index finger. With a combination of up-down movement of the index finger and left-right movement of the thumb, the contact of the thumb and the index finger can create 2-dimensional positioning. So we use this 2-dimensional interaction for our tip-tap. This potential two-dimensional input space looks like this. We make the space discrete with 3 positions on the thumb and 3 on the index. This means different combination of the thumb to finger touch create a 3 by 3 matrix like this, or like this. This can detect 9 different input positions. This 2D spatial configuration makes it natural for interaction like joystick-like control or 3 rows menu selection. To design our tip-tap, we conducted another study to answer 2 questions. The first question is, what is the performance of tip-tap with and without visual feedback? To measure the performance of tip-tap, we created wired tip-tap prototype. We used a simple mechanism to detect the touch event reliably. The finger touch event completes the circuit, and we measured the current between the index finger and thumb to detect the contact. The second question is, what kind of battery-free haptic feedback is suitable for tip-tap? To answer this question, we created 3 types of haptic feedback for our experiment system, which is magnet, bump, and smooth. We recruited 12 right-handed participants, and all of the participants used all 3 haptic types. The order of the haptic type was counterbalanced, and the experiment consists of 2 feedback types, visual feedback and non-visual feedback. The participants wore the fingerpad on their right hand and hid their hand inside of a box. In a visual feedback task, the position to be selected was shown on the left side of the screen, and the selected position was shown on the right. If the correct position was selected, it moved to the next task automatically. In a non-visual feedback task, when any position was selected, just a gray box was shown to indicate a touch event. The participant hit the space key to confirm the selection. All of the participants finished the visual feedback task first and then complete the non-visual feedback task after. So this is the task completion time. So in a visual feedback task, using smooth contact was significantly faster than using bump contact. In the non-visual feedback task, there was no significant main effect for haptic on the task completion time. In terms of input accuracy, in this case, higher is better. Using smooth and bump was significantly better than using magnet. In summary, contrary to our expectation, a smooth contact design with no haptic feedback design worked better than the others. So we choose smooth surface as a tip-tap haptic. So now we have 3 by 3 thumb pads to side of the index finger interaction with smooth contact design. Our next question is, how can we detect this 3 by 3 contact without battery? As a battery-free sensing mechanism, we used RFID. A passive RFID tag are battery-free and consist of antenna and chip. As long as the length of the antenna matches to the wavelength, the antenna can be very simple structure. For example, if just 2 straight wires attached to the chip, they work as an antenna too. When the RFID tags are available in the reader's detection range, the antenna receives the reader's radio wave and power up the chip to respond the unique ID to the reader. So to power up the chip with radio wave, the chip needs to be connected to antennas at each end. So that means if the chip is connected to a just half antenna, the reader cannot detect the tag. However, if we create 2 sets of the tag with half antenna and connect them in series, the reader can read both chips at that time. Moreover, if we connect more than one chip with a half antenna in parallel, and connect it to another half antenna, the chip connected to the other antenna can be detected like this, or like this. So in this way, we can detect any combination of the chips. So we found it can detect up to 3 chips each side reliably. So this is our final prototype, tip-tap on grab. So we used flexible wire as RFID antenna, and it is attached to the back side of the grab. As soon as you wear the grab on your bare hand, so you can start to interact. So with this configuration, the maximum detection range is around 4 meters. The original detection range of the chip we used here was 7 meters. We think the shorter range was because tip-tap is powering 2 chips at the time. So, and also placement of the RFID near the human body also affected the detection range. We also prototyped a temporary tattoo version of tip-tap, as I showed at the beginning of the talk. So we cut the copper tape in a custom antenna shape and embedded it into a temporary tattoo sheet. So in summary, I propose tip-tap, which is a 2-dimensional fingertip input techniques based on 2 user studies and Abari free recognition method using a novel configuration of RFID antenna and chips. So this is the end of my talk, so happy to take any question.
This is really interesting work. Thanks for the presentation. I was wondering actually what is the main factor that's limiting the spatial resolution? Could you somehow easily increase the density of your contacts that you have here? And thinking even further, could you foresee possibly some way for future work of how you could get continuous input along one dimension or even along both dimensions?
So you mean for the detection or for the input?
For the touch input, yeah.
Input. So for input, we actually tried, we tested with 4x4 combination first. But actually, so then we did the experiment, and it was actually hard for participants. So I, as the researcher, could detect the 4x4 position almost a perfect 100%. But for the participant, for the first time, they, of course, they practiced a little bit at the beginning of the trial, but the recognition rate was about 50% in average. So it takes a little bit of time to learn to point the correct position if it is more than 3 positions.
Hi, Valkyrie Savage, Tactual Labs. I find the outcome of your study really interesting, that the haptic basically the haptics were not valuable, that the smooth input was more useful. So what I took away from that is that for this area, proprioception is more important than haptics. But like, what do you take away from that?
Yes, so it's a good question. So yes, that actually our expectation. So we thought the magnet or bump condition should be better, and actually people liked the magnet condition as well. But the reason that the magnet was slower than the others was when you are trying to touch the certain position, because of the force of the magnet, the finger was forced to touch at the certain position without their intention before they actually decide where to touch. So then it's basically make more mistake. Then they have to pull out the finger to change the position. That also made it slower.
We have time for one quick question.
Thanks for this. Very interesting. I'm wondering if you could share some of your thoughts on potential applications given the requirement of a distance to the RFID reader.
Yes. So one of the application could be because this tip tap can be implemented on the glove. So maybe you can wear the glove in the sports gym, and while you are on the treadmill or like a cycling machine, you can control the music or your the monitoring system without changing your position. So that is one.
Thank you.
All right, let's thank the author once again. And if you have any other questions, you can find them at the end of the session.